Hello everyone, I am Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about biasing of a junction diode. So we have discussed few topics in the semiconductor devices, and today we are going to discuss about the biasing of a junction. And let us see the brief outline of how we are going to discuss about it. First, we'll see what is a PN junction diode and its working. Then we will understand the need for biasing of a diode. And then discuss about different types of biasing, the forward bias and the reverse bias. Coming to the PN junction, a P-type semiconductor material is placed with an N-type semiconducting material. Because we want a PN junction diode, we have already seen in the previous topics about how a PN junction is formed, and there are different methods of formation of PN junction. You can refer to that video for the formation of a PN junction. Here we are only mainly focusing on the working of a PN junction diode. So we are placing a P-type material, say this is P-type silicon, and this is N-type silicon. So a P-type material is placed along with an N-side material in such a way. How we are placing them? The atoms of the P-type combine with the atoms of N-type across the surface of contact. So this is the surface of contact for P and N. And the atoms of P-type will combine with the atoms of N-type. And such a junction, this junction that is formed, we are calling it as PN junction. Now let us see how the movement of charges takes place after the junction is formed. So we have seen the formation of a junction when two separate P-type and N-type materials are brought together. Now when I talk about P-type, P-type means a semiconductor material which is doped with a trivalent impurity. We call it as P-type semiconductor. And in P-type semiconductor, the majority carriers are holes. So these dots, the white dots here denotes the holes. So in P-type, holes are the majority carriers and electrons will be the minority carriers. When it comes to N-type, how we are getting an N-type? By doping it with a pentavalent impurity. Pentavalent impurity means an impurity which has 5 valence electrons. So when we are doping it with pentavalent impurity, there are more number of electrons. For each atom that we are doping, there are extra electrons that are generated. So the majority carriers in N-type are electrons and the minority carriers are holes. So what we need to understand, in P-type, holes are the majority carriers, and in N-type, electrons are the majority carriers. So now after the junction is formed, as the N region has high concentration of electrons and the P region has high concentration of holes, the electrons diffuse from N side to P side. So we need to understand what is diffusion here. Diffusion is a process of movement of charge carriers always from a higher concentration to lower concentration. So now if we see, the N-type is having more number of electrons. So the majority carriers here are electrons. So these electrons, because they are more in number, so they start diffusing onto the P side. So here these electrons start diffusing like this. And this gives rise to diffusion current. The current that is obtained because of this diffusion process, we call it as diffusion current. And this happens because of the concentration difference, means the difference in concentration of electrons in N-type and P-type. Now, when the electrons and holes move to the other side of the junction, they leave behind exposed charges on the dopant atom sites, and which are fixed to the crystal lattice and they are unable to move. Means what we try to understand here is, when an electron from here is moving on to the p side, then what happens? It will leave a positive dopant atom site here, which is fixed to the crystal lattice and it is unable to move. So all the electrons that have moved on to the p side, because of that, there are positive ion sites here and they are fixed to the lattice and they are unable to move. So we call them as immobile ions. So what happens here is, on the N side, we have the positive ion sites, and on the P side, because the holes have moved on to this side, so we have negative ion sites here. So on the N side, we have positive ion cores that are exposed, and on the P side, we have the negative ion cores that are exposed. So because of the movement or because of the diffusion of charges, that is electrons from the N side onto the P side and holes from P side onto the N side, they leave dopant sites, no, positive and negative ion sites, and we call them as immobile ions. So this region is now having only immobile ions. So now what happens when there are immobile ions? So an electric field is formed between the positive ion cores and the negative ion cores. Whenever there is a separation of charges, we know. So here on the N side, we are having the positive ion cores, and on the P side, we are having the negative ion cores. So there is an electric field that is developed. So we are denoting it like this. So this is positive and this is negative. There is an electric field that is developed because of these immobile ions that are deposited on either side of the junction. Now this electric field that is developed, it sweeps the charge carriers out of this region. Means there will be no more charge carriers in this region, or I can say that this region is depleted of charges. So we will call it as depletion layer. This layer, now we call it as depletion layer. Depletion layer means a region where there are no free charges, because the electric field that is developed due to these ions, they are removing the charges. So all the charges are swept away and we are having this depletion layer which is depleted of charges. The thickness of this layer is very small. It is of the order of 6 into 10 power minus 6 centimeter. Now a barrier potential VB due to the electric field E is formed at the junction. Now this gives rise to a barrier potential, and this potential we call it as contact potential or the junction barrier. Why we are calling it as a barrier? Because now once the potential is formed, there is an electric field that is developed and which gives rise to a barrier potential. Why we are calling it as barrier? Because this barrier obstructs the further movement of electrons and holes across the junction. Because of these negative ions, the further movement of electrons is stopped. So if electrons have to move, they'll have to overcome this barrier and go. Otherwise, they cannot move forward. So there is a barrier that is formed which stops the further movement of electrons and holes onto the other side. So as the diffusion of charge carriers from both the sides continues, the negative ions are forming a layer of negative space charge region along the p side. Similarly, a positive space charge region is formed by the positive ions on the n side. So what we are seeing here, we are seeing a positive space charge here on the p side, and here we are seeing a negative space charge on the n side. So because of this, what happens is there will be drift of the charges. The positive charge region will attract electrons from the p side. So here on the n side we have the positive charge. So this positive charge here is obstructing the further movement of electrons from n to p, but this will attract the holes from the the electrons from the p side. Electrons are the minority carriers in p type. So these electrons which are minority carriers in the p type will now start drifting towards the n side. And the same way, because of the negative space charge region here, the holes that are present in the n type, which are minority carriers, will slowly start drifting towards the negative space charge region. So what we see here is the electron drift is from p to n, and the hole drift will be from n to p. So what we are understanding here is the diffusion current. If you see, diffusion is always from higher concentration to lower concentration. So the holes will diffuse from p to n, and the electrons will diffuse from n to p. But when it comes to drifting, electrons will drift from p to n and holes will drift from n to p. So they are exactly opposite in direction. But as this process continues, at one instant, these two may become equal. So when this becomes equal, there is no further movement of charges from p side to n side. Then what happens? Because of the barrier, we are observing that there is no movement of electrons and holes. So what we try to do is somehow, by some means, if we can bring the barrier or break the barrier, then there will be movement of electrons and holes. So what do we do? So this is the reason why we have to do the biasing. What is the need for biasing? Because the barrier is formed and we want to remove the barrier. So in order to remove the barrier and facilitate the movement of charge carriers across the junction, we do biasing. So in biasing, there are two types we are going to see. So the first one is forward bias. First one is forward bias. So in forward bias, what we do is the p-type region of the junction is connected to the positive terminal of a voltage source, and the n-type is connected to the voltage source negative terminal. So what we see here, till now what we have discussed, we have seen this is the p-type and n-type brought together. P-type is having majority holes and n-type is having majority electrons. Now, some of the electrons crossed the junction and moved on to the other side. And also the holes were moving on to the p side. Because of that, there is a positive space charge region that is developed on the n side and negative space charge region that is developed on the p side. And this forms a barrier. So we have seen that there is a potential barrier that is developed. And this region is depleted of charges. So we are calling it as depletion layer. So these terms are very important. You need to understand what a depletion layer is. A layer that is formed at the junction where the region which is depleted of charges, we are calling it as depletion layer. And then there is a barrier, the potential barrier that is formed, which obstructs the further movement of holes and electrons. Now what we are doing is, we want to overcome this potential barrier by doing an external supply. So this is what we are doing. We are connecting an external supply to overcome this barrier. So how we are doing it in forward bias? The P-type region, this is the P side, is connected to the positive. There is a tab key to just keep open or close the circuit, and this is connected to the positive. So when P is connected to the positive terminal of the external supply and N is connected to the negative terminal of the external supply, you say it is in forward bias. So now in forward bias, what happens? Due to the attraction of positive terminal of the source, electrons that participated in the covalent bond in p-type material will be attracted towards the terminal. So all these electrons, because this is positive, the electrons which were here before forming the covalent bonds, they will get attracted towards the p side. Means all the electrons will start drifting towards the positive terminal. And what happens because of that? A number of covalent bonds are broken and the electrons are shifted towards the positive terminal, and this results in electron concentration in the crystal closer to the terminal to increase. So the concentration of electrons towards the terminal will increase, and then they will recombine with the holes here. So recombination of holes and electrons takes place. So this is also one important term you need to understand. What is recombination? Recombination means the electrons that are drifting or moving, shifting towards the positive terminal. So once the bonds are broken, the electrons are free, and then they combine with the holes. So there occurs the recombination. Now, due to higher concentration of holes adjacent to the negative impurity ion layers, the electrons of the negative ions come out and they will recombine with the holes. And when these electrons will recombine with the holes, they will create new holes inside the layer. So what happens because of this? The width of the negative ion layer is reduced. So as you see, the recombination is happening inside the layer. The width of the layer keeps on decreasing. The width of the depletion layer keeps on decreasing. At one particular voltage, what happens? The depletion layer vanishes. Now, if you see the negative terminal, now what we have done, we have connected the N-type to the negative terminal. So what happens here? The free electrons in the N-type region will repel towards the junction. So this is negative, this is positive. And here you have the electrons. So these electrons, because of the negative charge, they will be repelled. Means they will be moving towards the junction where they are finding positive impurity ions. So these electrons will now combine with the positive ions here and generate free electrons inside the layer. So what happens again here? The width of the positive impurity ions is reduced because these electrons are going and recombining with them. So the width of the positive layer also decreases and finally it vanishes. So in this way, both the layers of the ions disappear and there will be no more depletion layer. So when we have discussed, when we have started with biasing, the very motive of biasing is to break the barrier, means to decrease the depletion layer and break the barrier. So how we are doing it in forward biasing? We have connected P to the positive and N to the negative of the external supply. And because of this, what is happening? The electrons from the N side, P side started moving towards the positive terminal, and the negative terminal is repelling the electrons on the N side and they are pushed across the junction. Because of this, there is recombination that is happening inside the depletion layer, and because of which the depletion layer vanishes. Now, when the depletion layer is vanished, when it disappears, the free electrons from the N-type can easily move on to the P-type, P region, and the holes from the P side can come on to the N side, and there is no obstruction for the flow of current. And then the PN junction will behave like a short circuit. So now coming to the reverse bias. So in reverse bias, what happens and how do we connect? So in reverse bias, the positive terminal of the voltage is connected to the N-type region and the negative terminal of the source is connected to the P-type region. So we'll see here, this is positive, this is negative. This is the external supply. External voltage or the external supply we are providing to overcome this potential barrier. Now, how did we connect? The positive terminal is connected to the N-type. So, this is the N side of the PN junction and this is the P side. The P side is connected to the negative terminal. So, it is exactly the opposite of forward bias. In forward, P is connected to positive, N is connected to negative. But here, the P side is connected to the negative terminal and the N side is connected to the positive terminal. So, when we are connecting like this, then we say that the PN junction diode is connected in reverse biased condition. So, now what happens? What is the phenomena that occurs? The positive terminal of the source is connected to the N region. The free electrons of that region are attracted towards the positive terminal. Now, what happens here is, whatever we have here, the free electrons in this region, they are attracted towards the positive terminal. So, in N-type, we have more electrons. So, these electrons will get attracted towards the positive side. And because of that, what happens? More and more electrons getting attracted towards this. There are more and more positive ions. If you can see in the figure, it clearly shows that more and more. Before there were only 2 layers we have seen. Now, because of the movement of electrons from here getting attracted towards the P side, more and more layers of positive ions are formed. Okay, so more positive impurity ions are created in the depletion layer, which makes the layer of depletion thicker. And again, the same way, since the negative terminal is connected to the P side, electrons are injected into this region. So from here, because this is negative, there are electrons that are injected. So this layer also increases. So ultimately what happens here is, the width of the depletion layer keeps on increasing. So if you can see the width of the layer is increasing because of reverse bias. Now, when there is no voltage applied across the PN junction, the potential developed across the junction is around 0.3 volt for germanium and 0.7 volt for silicon at a temperature of 25 degrees Celsius. Now, if the reverse bias voltage across the PN junction is increased, the barrier potential developed across the junction is also increasing. So, as you increase the voltage, the width of the depletion layer goes on increasing. So, the PN junction is widened. Now, the overall width of the depletion layer increases with the barrier potential. And this increment of depletion layer will continue till the barrier potential reaches an applied reverse bias voltage. So, till that point, the width of the depletion layer keeps on increasing. So, after completion of this reverse bias depletion layer, there is no more drift of charge carriers, that is, electrons and holes through the junction, as the potential barrier opposes the applied voltage. So, it is opposing. So, there is no movement, but only the minority carriers will be moving from the N region and the P region. So, there will be a small current. We call it as tiny current. And this current is due to the minority carriers. Now, what we are seeing here is there is an increment in the barrier potential, and this will continue up to an applied reverse voltage, we thought. If the applied reverse bias is sufficiently high, means if it can overcome this potential barrier, then the depletion layer will disappear due to avalanche breakdown. So we call it as avalanche breakdown. Means at one particular point, if the applied voltage is more than the barrier potential, the barrier breaks down and we call it as avalanche breakdown. So what we have seen here, we will just summarize what is the need for biasing. If there is no bias, what happens? If there is forward bias, what happens? And if there is reverse bias. So in an electrical circuit, current flows more easily in one direction than any other. And when we do forward biasing, what it means? It means putting a voltage across the diode that allows the current to flow easily. Means it will reduce the barrier potential so that the current can flow very easily. And if you are doing reverse biasing, means the voltage, we are putting a voltage across the diode in the opposite direction. So the voltage with the reverse biasing does not cause any appreciable current to flow. So what we are trying to say is, in reverse bias, we are not getting any current. Of course, there is a small current due to the minority carriers. So we can use this for changing the AC current to DC current, or it can be used for manipulating the electronic signals also. Now let us try to understand these diagrams. In biasing of a junction, this is a PN junction. Energy diagrams we are going to understand. Energy level diagrams we can say, or energy band diagram. So in a PN junction, so this is P and this is N. There is a depletion layer that is formed, and this is the width of the depletion layer. So whatever phenomenon we have seen, because initially there is movement of electrons from here on to the P side and holes onto this N side, because of which there are positive ion sites that are created and there are negative ion sites that are created on the other side of the junction. And because of this, there is a barrier that is formed. So this potential barrier, we call it as VB. VB is the barrier potential between N and P. So this is at equilibrium when there is no external supply. Means this is open. We are not connecting any external supply, or I say this is unbiased condition. This is unbiased condition. So in unbiased condition, once the equilibrium is reached, there is no further movement of electrons and holes onto the other side. And if you see here, this diagram, ECP denotes the lower level of the conduction band on P side, and EVP denotes the topmost level of the valence band on P side. So P here represents the P side, and EC is for the conduction band and EV is for the valence band. So now when you are drawing the diagram for a PN junction, already we have discussed this in the energy band diagram, and this is ECN for the N side conduction band, and this is EVN. V always denotes the valence band and N denotes the N side. Now, what is the difference in the potential here is EVB. So, on both the sides, if you see, the difference is EVB. So, this is what we are understanding in unbiased condition. There is a barrier potential that is formed. Now, what we are doing in order to overcome the potential barrier, the first thing we have discussed is forward bias. So, we have applied an external voltage, and how we are applying it in forward bias, that is positive is connected to the P side and negative is connected to the N side. So, when we are doing forward biasing, actually what is happening is the barrier potential is lowered. So, VB is the potential, and VF we are calling it as the forward voltage that is applied, which tries to lower the potential barrier. So what is the resultant potential now? It is VB minus VF. So because of the barrier forward bias, what is happening? The barrier potential is lowered. Even if you see in the energy band diagram, ECP, EVP, and the difference here is reduced. It is becoming E VB minus VF. So here also it is the same, E VB minus VF. And now coming to the reverse bias. In reverse bias, what we have seen, we have connected the negative terminal to the positive and the positive terminal to the negative. So by doing this, what is happening here is the barrier potential increases because the width of the potential barrier is going on increasing because of the reverse bias. The resultant is VB plus VR. VR here denotes the reverse voltage that is applied. So even in the energy band diagram, if you see, here the barrier height increases. It is E into VB plus VR. Same on both the P side and N side. What we are seeing here is the barrier potential increases. So this is what we have seen. When the PN junction is unbiased, it is in equilibrium and the contact potential VB is Vn minus Vp. The contact potential appears across the region on both the P side and N side. Now, when an external voltage is applied, if we are doing the forward bias, that is positive connected to the P side and negative connected to the N side, the voltage Vf appears across the depletion layer and the resultant is given by Vb minus Vf. Vb minus Vf, what does it mean? Is the resultant potential is less than the barrier potential. Initially, the barrier potential is denoted by Vb and Vf is opposing this and the resultant we have is Vb minus Vf due to forward bias. And when external voltage VR is applied in reverse bias, means when P side is connected to the negative and N side is connected to the positive, it is in reverse bias. So because of that, what is happening here is it becomes VB plus VR. The electrostatic potential barrier goes on increasing. So it will be more than VB. By how much? VR. So the resultant is VB plus VR. So what we understand here is on application of forward bias, the electric field in the transition region reduces and the application of reverse bias increases the electric field in the transition region. That is what we have seen, VB minus VF and VB plus VR. And since the width of the transition region is proportional to the square root of the electrostatic potential barrier, the width of the transition region decreases under forward bias and it increases under reverse bias. So if you have any doubts or any clarification regarding this topic, you can refer to books Semiconductor Physics and Devices by Donald Niemann, or you can also refer to Semiconductor Devices and Physics by Simon Z and Ming Lee. Thank you and see you again.
Like, share and subscribe. Hit the bell icon for more updates.